Hi everyone, we are continuing our discussion on module 4 data communication, and right now we are in part 6. So far we discussed the multiplexing technique, particularly the frequency division multiplexing and wavelength division multiplexing in detail, and then we moved on to our discussion on time division multiplexing, starting with this variation called synchronous TDM, and we already see in the overall system design. Now we are continuing our discussion on the synchronous time division multiplexing technique, particularly on the concept of the framing and the overall system. We already discussed in part 5 what is happening at the sender side and what is happening at the receiver side, and in between we saw that frame structure also. Now we will see somewhat detail on the frame structure. So the transmitted data may have a format something like the figure below. So this is something we already seen in the previous discussion. So when the sender is sending, there is some kind of scan operation with which from each of the devices which are connected to the multiplexer, it will scan a particular unit of information, and together it will form a frame. So here we have a multiplexer with say n connections, n input connections, and from each connection I am taking one unit of data, and that unit may be I can take a bit by bit from like that. From the first input connection take a single bit, and second input connection take the next bit, like that you can take that. That is what is called bit interleaving. And in most of the cases we are using something called a byte interleaving, where from each of the input connection we will be taking a byte or a character, and together we will form the frame. Okay. So the frame is now containing say n bytes or n characters when it comes to byte interleaving. Or you can think of something bigger unit also, say 2 byte from each source I am taking, like that in any way. So in this way we are forming a frame, and frame by frame we will be sending the information through the common communication link to the receiver, and at the receiver side with proper synchronization in terms of time, like so whenever a frame is coming, so this is what is called a time slot. And what we are doing is we are dedicating a time slot for each and every source which want to communicate with a particular destination, and at a particular point of time this source may not want to send the data, or it is having some information to send, so that we can't guarantee. That means if you are looking at the time slot, it may be empty or occupied at any time. So that is a demerit here. Suppose the particular source don't want to send the data, then simply the slot will be wasted. We are not able to reuse it or utilize it efficiently, and such a variation is actually statical TDM. When we discuss statical TDM, we will see how this wastage of time slot is handled there. Okay, so that about the overall idea. Then the data are organized into frames like this. Each frame contains a cycle of time slots. That is what we see. And each frame, in each frame, one or more slots are dedicated to each data source. So for the data source 1, here one slot is dedicated. For data source 2, second slot is dedicated. But if you want, you can dedicate more than one time slots also for a given data source if needed. It may be for managing the data rate. Sometimes you are the multiplexer is connected with say for example 2 input connections or 2 sources, and one source is want to send data at a rate 2 times as that of the other one. So it is always better to give a more consideration to the source which want to send data with a higher data rate. So what we can do is, for the data source which want to send a higher data rate, we can allot the 2 slot, and for the other one we can allot 1 slot. So like that, if needed, we can allocate more than 1 slot for a particular source also. And such variation also we will see. As of now, you can assume like per each source we are allocating a single slot. Now the sequence of slots dedicated to one source from frame to frame is called a channel. For example, if you are looking at this particular figure, for source 1 this time slot is allocated, right? Similarly for slot 2 this slot is allocated. For the source 2 this slot is allocated. Now in the next frame also, for source 1 this first time slot is allocated. So if you are looking at the this kind of a diagram, you can see that the first slot is for source 1, in frame 1, in frame 2, in frame 3, like that. In all the frames, the first slot is exclusively for source 1, and together all these slots that are assigned to a particular particular source is make what is called a channel. So channel is, in this case, channel is nothing but the part of the overall medium that is dedicated for a particular source, that's all. So in this case, this one, all these one, similarly you can imagine the next frame, there also slot 1 will be there. All these 1 slot together will make the channel for source 1. Similarly, all the time slot 2 marked like this together will form the source for channel for source 2. Okay, some another terminology. Now, what about the length of a particular slot? What is duration of this slot? And that is equal to the transmitter buffer length. That depends, right? Transmitter buffer in the sense, suppose a multiplexer is connected with the n input lines. With each input line there will be buffer attached at the end, right? And within that buffer the data is getting buffered, and from there by a scan operation we are collecting the data together and we are sending it to as a frame. That system we already seen. And in that case, depending on the the length of the buffer, the slot length will be determined. So buffer, so if we are looking at bit interleaving, the buffer will be buffering one bit at a time from a particular source, so that the buffer length is 1 bit, and that 1 bit you are taking and you are making the frame. From all the input connection, we will be taking 1 bit, and together we will make the frame. And in that case, the particular buffer connected with each and every input line is of length 1. Similarly, if you are thinking about the byte interleaving or character interleaving, where from each buffer, each and every buffer which are connected to each input line is will be buffering 1 byte at a time, 1 character at a time, and now the scan operation will take those bytes together and will form the frame. Okay, so that is how we are fixing the slot length. The idea is the slot length has to be equal to the buffer length, then only we can take it. So as long as the buffer is getting emptied, the source will be filling the buffer with the next unit of data, that may be 1 bit or byte, and immediately it will be taken in the next scan. So like that it will keep on doing in such a way that the individual input connections are not getting a feel like it has to wait. Simply, what is the data rate of each and every individual connection, and the same data rate we will provide in the for the outgoing link also. So together that smoothness will be maintained. Now at the receiver side, what is happening? So how the receiver is getting synchronized with the source. So as the name says, it is synchronous TDM, right? So how the receiver is correctly synchronizing with the source, and it will take the data from a particular source. So if you are looking at the frame at the receiver side, these frames will be received, right? Now from the frame, correctly it has to take say slot 1 for destination 1 being with which source 1 is being connected. Similarly, slot 2 is for destination 2 with which source 2 is connected. Like that, how it is going to take the data. So for each input source, Mi of t, and this is from the system view. The overall TDM system, we saw a diagram where what is that Mi of t, the input that is coming from the input line ith line, and for all such a source Mi of t, there is an identical output destination that will receive the data. So n sources are connected at the sender side, there should be n receiver at the receiver side also. So source 1 will be connected with the receiver 1, source 2 with the receiver 2, and the portion of data that is being communicated from source 1 to destination 1 is what we call as channel. And a particular channel is spread over different frames. Everything we already see. Now the synchronous TDM is called synchronous, not because the synchronous transmission in the sense the sender and the receiver are synchronized with say a common clock. It is not like that. It is mainly because the fact that the time slots are pre-assigned to source and fixed, that we already seen. Slot 1 is for channel 1, slot 2 is for channel 2. So whenever the frame is being received at the receiver side, it will take, we already know this time slot length in advance, okay, and that also we will see how we are fixing the slot length. So once we know the slot length, whenever the receiver is receiving a frame, it will take the data till it is reaching that slot length, and that will be given to say if it is slot 1, say it is given to destination 1. Now the next slot data will be delivered to destination 2. So like that it will properly do, and that is how the synchronization achieved, in the sense the slots are pre-assigned. From the sender point of view, say there are 6 senders want to send the data, there are 6 slots allotted in a frame. Similarly, at the receiver side, frame is coming, and it will divide that frame into 6 slots, and each slot, the information contained in each slot will be delivered to that particular receiver. So that is how we are achieving this synchronization. And at the same time we are having the problem, like sometimes the slots are there, but we are not able to send some information because the source don't want to send the data, so that will lead to empty slots, which is a wastage of resources. So hope you understood what is synchronous here. So that is how we are achieving the synchronization. Slot 1 is for source 1 to destination 1. Slot 2 is for source 1 to destination source 2 to destination 2. So like that there is a predefined assignment, and that assignment accordingly the sender will be creating the frame, and at the receiver side also the frame will be splitted into time slots properly, and from each slot correctly the data will be taken and delivered to the actual destination for which it is intended for. Now within a frame also there is something called that, those things we will come soon. We have to differentiate one frame from the previous one, and that is also needed, because if some part of because everything is finally communicated in the form of zeros and ones, and which further will be moving in the form of some digital or analog signal. So whatever it is at the receiver side, simply some signals are coming. How it is going to identify that it is a frame, it is a new frame? So some kind of frame delimiter, start of frame delimiter, end of frame delimiter is also needed, and that also we will provide, and with that we will identify each frame. Now once we are getting the beginning and end of a frame properly, we are able to identify this as a particular frame. Then we can by taking the slot length, we can take and divide the information within that frame into different slots, and in a correct way we can deliver the portion of information that is there in a particular time slot to that particular destination. So that is how we are achieving synchronization, and doesn't mean that we are having some kind of clock synchronization happening. It is not like that. So time slots for each source are transmitted whether or not the particular source want to send some information. This is of course the case with FDM. So if you are looking at frequency division multiplexing, there also the total frequency you are dividing into n channels, right? And we are dedicating each channel for a particular pair of source and destination, and that time if that source don't want to send some information, it will be simply wasted. So same problem is there in FDM also and in synchronous TDM also, but it is not there in something called statistical TDM, and we will see how it is achieved. So in both cases the capacity is wasted to achieve simplicity of implementation. So if you look at the implementation part, the TDM and FDM are better. They are having very simple implementation compared to, so every time you have to compare, then only you will get that picture clear. Why it is simple means when we are comparing it with other existing system which achieve this, where there is say no capacity wastage, which achieved better utilization of the channel. In that case the overall design may be complicated compared to this. Okay, that may happen. So keeping simplicity and we want to avoid wastage, that will be something difficult to achieve. So next we will see the system called statistical TDM, where you can see that this kind of a capacity wastage is not there. Simply we are able to utilize the total channel capacity. That means whenever we want to send some data, then only the slot will be allocated. There is no predefined allocation, so the slots will be allocated dynamically. So that is what is happening in statistical TDM. So but how it is achieving that? there comes some complexity. Okay, so the overall design will be somewhat more complicated than what we already seen in FDM or synchronous TDM. So that is why when we are trying to compromise the capacity, we are getting actually simplicity of implementation. So if you are ready to compromise the simplicity on implementation, if you can put some more complex effort, capacity could be saved. Okay, that kind of a design we will see. Now we will see a typical example of a time division multiplexing. So where with this multiplexer, say here 3 input connections are there. So this is from a particular source 1, source 2, source 3. So it's like the 3 input connections, and see each of these input connection want to send some set of information, and see the duration of a particular frame or whatever it is, unit of information here. This is t second, t second, t second. Okay, so if you are the t in the sense, this is something you have to note down. So what is the time taken to send this unit of information called a1, that is t. Similarly, the uniform time we assumed, the another unit of information a2, that is also sent at time t. The total time taken to send this a2 is t. It may be a byte, it may be a bit, or it may be more than 1 byte, whatever it is. So let me call it as a unit of information. Similarly, for a3 t. So like that, every source is generating data, unit of data, and the time taken to generate a particular unit of data is t. Now what we are doing is, from each source, by using some kind of a scanner here, we will collect, and at the end of the source we have that buffer also, that concept, everything you have to visualize now, that overall system. So if it is simply shown like a multiplexer, but inside that multiplexer we have buffers here and a scan operation here, and from all the buffer, first this a1 will be buffered, then on the same time from source 2 b1 will be buffered, and from source 3 c1 will be buffered. Now the scan operation will collect a1 b1 c1 together, and it will make the frame like this, a1 b1 c1. Okay, this is framework. Then the buffer 1 will be filled with a2, because this is already delivered. Buffer 2 will be filled with b2, and buffer 3 will be filled with the c2. And now the scan operation will collect a2 b2 c2 together, and it will make the frame 2. Similarly, a3 b3 together and frame 3. So like that it will continue. Now what is the total time taken to send this frame as a whole? See, the frame is actually containing a unit of information from all the input sources. So the total time taken for the frame transmission is t, and that t is nothing but this t. Okay, so what we can conclude, this is a very important concept here, same concept I am trying to explain previously also. What is the time taken to send a particular unit of information for each source? That same time we are making as the time taken to send the particular frame through the common shared medium. Now how we are able to achieve it? By simply increasing the data rate. For example, what is the overall data rate? Data rate means the number of bits transmitted per second for this source 1. What is the data rate of source 2? What is the data rate of source 3? Here we assumed uniform data rate, but variations are also possible, and that we will see how variations. So far we assumed uniform data rate. So when it comes to variation, we will see how it is to be handled. So suppose this is sending information at say 40 kilobits per second. Here it is another 40 kilobits per second. Here it is another 40. So 40 together 120 bits per second should be the speed of this outgoing link. Then only we can achieve the time taken to send a unit of information from each channel, and the time taken to send a frame to be t. Okay, and you know how to calculate this duration of time. Let me say the data rate is 40 units per second. Then 40, simply I am taking an example, or okay, data rate is 10 units per second. A unit can be bits per second, 10 bytes per second, depending on whether you are using bit interleaving or byte interleaving or some other technique, whatever it is. So suppose I am simply using the term unit. Unit can be bit or byte, whatever it is. So I have a input line with a data rate of say 10 or some x. Okay, let me take as 10 unit per second. Now what does it mean? 10 units per second means in every second 10 units are transmitted, and the time taken to transmit a particular unit of information is what is that? In 1 second 10 units are transmitted. Then for transmitting 1 unit, how much time? 1 by 10 seconds are needed. Same concept. Okay. Now what we are trying to do is, so here say from source 1 the data rate is let me take a 10. Okay, just try to visualize. So you write down somewhere, I'm not able to write here. From source 1, suppose the data is delivered at a rate of 10 unit per second, from source 2 another 10 unit per second, and from source 3 another 10 unit per second. So now what happened is the time taken to send a particular unit of information is 1 by 10, and that is what is taken as t here. Okay, now as I already told you, what could be the data rate of the outgoing link? 10 plus 10 plus 10, or 3 times this, because 3 input connections are there, so that the outgoing link should be of 3 times the data rate or capacity of individual ones. So the data rate of the outgoing link has to be 3 into 10, that is 30 unit per second. In this example, if I am taking the input, each input line is of capacity 10 unit per second, the outgoing link is of capacity 10 into 10 plus 10 plus 10, 30 unit per second. Now when I am taking the input connection to be 10 unit per second, the time taken to send a particular unit of information is 1 by 10, and that is what is shown here as t. Let it be t. Now for the outgoing link, what is the data rate? 30. Okay, and the 30 unit per second. Then what is the time taken to send a particular unit of information? It will be 1 by 30. Okay, and in the position of 1 by 30 we are getting, so 1 by 10 is actually our t, right? So here we are getting 1 by 30, so this will be this t by 3, because something 1 by 30 you can write like 1 by 10 into 1 by 3. So that 1 by 10 I taken like a t, so 1 by 3 will be t by 3. Hope you got an idea about how this t by 3 is coming. So otherwise simply understand like that. What we are trying to say, each unit of information is taking a time t, and we are trying to make the outgoing link capacity in such a way that the total time taken to send a frame as a whole is whole as t. So make this concept clear. This is t and this is the frame. So that is why we are getting that without any interruption. Whenever the data is ready at the from this particular source, it is able to send that to the outgoing link without any waiting actually, because this is t and this is also t. That is why. So the all together, what is the total speed? That speed we are achieving in a single channel, single outgoing link. So if the total time taken to send a particular frame is t, then what will be the time taken to send a particular unit of information within the frame? So within a frame, as we have 3 input connection, 3 unit of information will be there. So for particular unit of information, maybe a bit byte or whatever it is, it will be t by 3. Okay, so like that you can, or you can take an example like what I explained, say 10 or 20 something, and together what is happening here and what is time taken. If data rate is 10 bits per second, then what is the time taken to send a particular bit, or what is the time taken to send a particular unit of information? That will be 1 by 10, and that is t. So and when it comes to the outgoing link, the total data rate will be making a sum of all these 3. In that example it will be 30 unit per second. So the time taken to send a particular unit of information, say a1 b1 or whatever it is, in the outgoing link will be 1 by 30, and that is nothing but this 1 by 10 we taken as t, so it will be t by 3. Like that. So data are taken from each line in every t second. So at the end of t second we are taking data from that buffer. Each frame is 3 time slots, and each time slot duration in the outgoing link is now t. So this figure I taken from Frozen textbook. Some kind of mistakes are there, like this printing mistakes. So this is t by 3. Okay, this is t by 3 seconds. And whatever things I explained in the previous figure, I listed here. Just go through this. In synchronous TDM, a round of data units from each input connection is collected into a frame. So within a frame, we are having information from all the sources taken in a round robin manner, like source 1, source 2, source 3, again source 1, source 2, source 3, like that. So if we have n connections, a frame is divided into n such as time slots, and one slot is allocated for each unit, assuming uniform data rate and all. Otherwise, maybe for a particular source we may be allocating more than one time slots also, but here we assume if there are n connection, for each connection we are allocating a single slot of time, so totally there will be a frame containing n slots, and allocated for each unit and one for each input line. So if the duration of the input unit is unit of information like A1, A2, like what we seen there is T, then the duration of the slot has to be T in, and this T in is nothing but T divided by N, like that. T in, I don't know whether it could be again a printing mistake. Either it is T by N, that is the correct value here. If there are n slots connected, in the previous example 3 slots connected, for the input the time taken for a particular unit is T, and for output time taken for the same unit of information is just T by 3 only. So in general it will be T by N, or you can denote that value by T in, and T in is nothing but T by N. Okay, you just take in anyway, and the duration of each frame is the frame as a whole, the duration is T. So actually we are trying to make the total duration of the frame to be T, and within to achieve that we are forced to make the time slot width as T by N. So unless the frame carries other information. So this is something I already told you, the frame as a whole will be having some kind of special pattern to distinguish it from the other frames. Okay, so we have to mark the beginning of a frame or an end of a frame. Then only continuously when information is coming, you can separate them into different frame at the receiver side. So if such additional informations are coming, then that also will be taking some space in the frame, so that the total time taken to send the frame will be slightly more than this T. Okay, to make that possible, otherwise it will be T. So when it is T, we are assuming that there is no extra information in a frame, but in reality it will be slightly more. The data rate of the output link must be n times the data rate of the connection to guarantee the flow of data. So to ensure the continuous flow of information from the source through the common carrier to the receiver, we should ensure that the data rate of the outgoing link is n times faster than data rate of the input lines. So like my example, like 10 bits per unit, 10 units per second, 10 units per second, 10 units per second, so that the outgoing link is having 3 into 10. So that is 3 in that example. Here it is n connections we assumed. So n times n into 10, whatever it is, the data rate of the input connection should be the data rate of the outgoing link to ensure the continuous smooth flow of data. So in the previous example, the data rate of the link is 3 times the data rate of the connection. So likewise, the duration of a unit on a connection is 3 times the unit time slot. The time slot duration is 1 by 3 times that of the duration of a unit in the input line. So both relations are clear for you. So this is the conclusion from this entire explanation. So in synchronous TDM, having n input connections or n sources connected to it, the data rate of the link, in the sense the outgoing common shared link, should be n times faster if n devices are connected, and the unit duration is n times shorter. Unit duration is slot duration. The unit of information within frame, or okay, in the previous example A1, A2, like that we have a unit of information from source 1, B1, B2, like that we have a unit of information from source 2, and finally similarly C1, C2, C3. And in a frame A1, B1, C1, like that we are collecting each unit of information from all the 3, and together we will make the frame. And that time the slot duration, the duration of a slot in a frame, or duration of a unit in the outgoing link, whatever it is, that is n times shorter, and the data rate of the outgoing link is n times faster. So in that way you have to construct your synchronous TDM so that is where that synchronization is achieved. So if you are not ensuring this, there is no synchronization, then the receiver is not able to synchronize and take the information correctly back. Okay, So to maintain that flow of data and to maintain that synchronization, these two things you have to keep in mind. Accordingly, you have to design your system. So hope you got an overall idea, and we will see certain problems from this, so that this concept will be more clear. So in the problem, this last line is very important. This concept is what we are applying. Just remember this: for the outgoing link, the total data rate, the total capacity should be n times as that of the rate of the means connections, input connections, assuming uniform data rate. If the data rate is varying, accordingly in that case also you should find out, and that we will see another with some another set of examples. And similarly, the duration of a particular slot in or within frame slot or unit of information in the outgoing link, whatever it is, should be n times shorter. Okay. Thank you, and we will see more problems on this synchronous TDM in the next part.